We are back today discussing more about complex numbers. In the previous lesson, we looked at the complex plane and how to write a complex number in polar form. In the pre-video activity, you applied your expert algebra skills to completing operations with complex numbers in rectangular form. In this video, we'll be performing operations on complex numbers in polar form. Let's get started. Operations with polar coordinates are used in the real world to work with systems that involve circular or rotating motion, like radar tracking, designing roller coasters, and mapping out sound waves. Polar coordinates make it easier to calculate positions and movements around a central point, which is especially useful in fields like engineering, navigation, and physics. In the pre-video activity, you practiced applying some basic algebraic rules such as combining like terms and distribution in order to add, subtract, and multiply complex numbers in rectangular form. We'll be using these skills again as we derive the formula for the product and quotient of complex numbers in polar form. First, we're going to tackle the process for adding and subtracting complex numbers in polar form. As a reminder, a complex number, z equals a plus bi, can be written in polar form as z equals r times cosine theta plus I sine theta, where r is equal to the modulus of the complex number, and theta is the angle of the complex number. So, how do you think we add two complex numbers, z and w? This is a bit of a trick question because we actually rewrite complex numbers from polar form to rectangular form in order to add and subtract. Do you remember how to rewrite z and w into rectangular form? To rewrite z and w in rectangular form, we evaluate the trig functions and distribute r. So, for z, cosine of 30 degrees is square root 3 over 2, and sine of 30 is 1 over 2. Distribute 3 and you get z equals 3 square root 3 over 2 plus 3 over 2i. For w, cosine of 180 is negative 1, and sine of 180 is 0. Distribute 2, and we get w equals negative 2 plus 0i, or just negative 2. Now we just add or subtract by combining like terms. Pause the video and evaluate z plus w and w minus z. Check your work. For z plus w, I start with 3 square root 3 over 2 plus 3 over 2i minus 2. 3 square root 3 over 2 and negative 2 are like terms. To combine them, I make a common denominator of 2. Note that 3 over 2 includes I and cannot be combined with any other terms. So my final answer is z plus w equals 3 square root 3 minus 4 over 2 plus 3 over 2i. For w minus z, I start with negative 2 minus the quantity 3 square root 3 over 2 plus 3 over 2i. Distribute this negative. Again, 3 over 2i doesn't have any like terms to combine with, but I'll combine negative 2 with negative 3 square root 3 over 2 just as before. And the final answer is w minus z equals negative 4 minus 3 square root 3 over 2 minus 3 over 2i. Now, the task we are challenged with is to find the product of complex numbers written in polar form. When complex numbers are given in polar form, it's true we could rewrite them in rectangular form, then multiply. However, there is actually a simple formula to follow for multiplying complex numbers in polar form, and we're going to use algebra and trigonometric identities to derive it. Let's start by defining our two complex numbers. We'll call them z1 and z2. Notice, I use alpha and beta instead of theta. This is simply for convenience and to help me keep the two complex numbers straight. So we're finding the product z1 times z2. Since we are multiplying, we're able to move each of these terms around to make our process a bit easier. For example, we'll bring the two r terms to the front, since they are monomials. How do we multiply two binomials? Yes, we distribute, just like on your pre-video activity. Be careful on this step. We are not distributing the r terms. We are expanding this binomial multiplication. There are many ways to complete binomial multiplication, so if your steps look different than mine, but you end up with the same answer, that's okay. My first distribution step is to multiply each term in the first binomial by the entire second binomial. Then my second distribution step is to distribute cosine alpha and I sine alpha into these binomials. The result is r1 times r2 times cosine alpha cosine beta plus I cosine alpha sine beta plus I sine alpha cosine beta plus I squared sine alpha sine beta. Pause your video now if you'd like to review any of these steps before moving on. Normally, after binomial multiplication, we are able to combine like terms to simplify. Do we have any like terms here? No. Since our angles alpha and beta are different, we actually don't have any like terms to simplify, but there is something we can simplify. Do you know what it is? Did you say I squared? If so, you're exactly right. I is the square root of -1, which means that I squared is actually -1. So we can substitute -1 for I squared, which changes this to minus sine alpha sine beta. At this point, in order to simplify further, we need to turn to our sum and difference identities. You worked with these identities in Unit 6 to solve trigonometric equations and prove other trig identities. Do you see any identities that we might use to simplify our current problem? If I rearrange some terms, I can see that cosine alpha plus beta will substitute for this piece, and sine alpha plus beta looks a lot like this piece, except for the I. Any ideas for what I can do with the I? Since both terms have an I, it can be factored out. And now we can substitute using our cosine and sine sum identities. And there you have it. Pat yourself on the back because you just derived the formula for finding the product of complex numbers in polar form. You can imagine how this shortcut will come in handy as we find the products of complex numbers. Now, let's see this formula in action. Given two complex numbers in polar form, w and h, find their product. Pause the video if you'd like to try this on your own. Otherwise, keep watching to follow along with me. To find the product, the shortcut says to multiply the moduli. And then we add the angles. So w times h equals 3 times 2 times cosine of 135 plus 90 plus I sine of 135 plus 90. Now just simplify. And we get w times h equals 6 times cosine of 225 plus I sine of 225, and that's it. That's the answer. Now let's talk about division. Division can get tricky when a complex number is in rectangular form because we can't divide by an imaginary number. If you're interested in seeing division of complex numbers in rectangular form, check out the extension activity in the lesson materials. However, we actually have another helpful shortcut for division of complex numbers in polar form. We won't go through the derivation here, as it is almost identical to the process we just did for the product. If you are interested in tackling it, it's included as an extension activity for this lesson. For two complex numbers, z1 equals r1 times cosine alpha plus I sine alpha, and z2 equals r2 times cosine beta plus I sine beta. The quotient z1 over z2 equals r1 over r2 times cosine of alpha minus beta plus I sine of alpha minus beta. Since this is pretty similar to the rule for finding products, I'm going to let you try this first example on your own. Find h over g if h equals 3 times cosine 120 plus I sine 120 and g equals 5 times cosine 60 plus I sine 60. Pause the video now. Check your work with me. The formula says to divide the moduli, giving us 3 over 5. Then subtract the angles 120 minus 60 and simplify to write the quotient of h over g as 3 over 5 times cosine 60 plus I sine 60. Is that what you have? Great! The last two operations we'll look at with complex numbers will determine powers and roots. French mathematician Abraham de Moivre was actually one of the first mathematicians to use complex numbers in trigonometry, and he developed the theorem that we will use to find the powers and roots of complex numbers in polar form. Let's use our formula for the products of complex numbers to see how de Moivre arrived at this theorem. Since exponents or powers are just repeated multiplication, we can use the product rule to find z squared when z equals r times cosine theta plus I sine theta. Z squared would be z times z, which equals r times cosine theta plus I sine theta plus theta. Let's simplify this since we have some like terms. Interesting. So if I raise z to the second power, I end up raising the modulus to the same power and then multiplying the angle by that value, in this case 2. I wonder if that holds for all powers of z. Let's try it again with z to the third power. Z to the third power is just z times z squared, and since we just determined that z squared is r squared times cosine 2 theta plus I sine 2 theta, we'll use that in our product rule. So z times z squared is r times cosine theta plus I sine theta times the quantity r squared times cosine 2 theta plus I sine 2 theta. Apply the product rule. Now simplify. Do you see the pattern emerging? This is exactly what de Moivre saw, which led him to formulate and prove this theorem for finding powers of complex numbers. For any complex number z equals r cosine theta plus I sine theta, z raised to the n power is r to the n power times cosine n theta plus I sine n theta. Let's try an example. Find h to the fourth power when h equals the square root of 3 cosine 60 plus I sine 60. Pause the video and try this now. Review your work with me. To find h to the fourth, I raise the square root of 3 to the fourth power and multiply the angle 60 by 4. You could use a calculator here, but I know that the square root of 3 to the fourth power is the same as the square root of 3 squared times the square root of 3 squared, which equals 9. And 60 times 4 is 240. So h to the fourth power is 9 times cosine 240 plus I sine 240. How'd you do? Being the curious mathematician he was, de Moivre realized he could also use this formula with rational exponents, which means he could determine the roots of a complex number. First, let's figure out what we mean by roots. In Unit 2, you learned the fundamental theorem of algebra, which states that for a polynomial with degree n greater than or equal to 1, the polynomial has exactly n complex roots. Note that complex roots might be pure real roots, where the imaginary part is 0, pure imaginary roots, where the real part is 0, or complex, in which both the real and imaginary parts are not 0. Why do we need the complex roots of a number? Well, roots of a complex number are evenly spaced points on a circle in the complex plane. These roots reveal the symmetry and periodicity of solutions, which is useful in fields like signal processing and wave analysis. So how do we find the roots of complex numbers? Well, let's consider the equation x to the fourth power equals 8. Based on the fundamental theorem of algebra, there must be 4 complex roots, which might be pure real, pure imaginary, or complex. In the past, when we've solved equations like this, we've simply taken the fourth root of both sides, but that method will only give us one of the roots we're looking for. In order to define all 4 complex roots, we need to rewrite 8 as a complex number in polar form and then apply de Moivre's theorem. Since 8 is a pure real number, I can express it as 8 plus 0i. Then I'll rewrite 8 plus 0i in polar form. The modulus of 8 plus 0i is the square root of 8 squared plus 0 squared. So r equals 8. And since this point, 8, 0, is on the x-axis in the complex plane, we can see that theta equals 0. So my equation is now written as x to the fourth equals 8 times cosine 0 plus I sine 0. Why did I do all that? Right, so that I can use de Moivre's theorem for finding the power of a complex number. If I'm taking the fourth root of a number, what is the rational exponent I would use? I would use 1 over 4. So I raise both sides of this equation to the 1/4 power. Now, apply de Moivre's theorem, and I get x equals 8 to the 1/4 times cosine 0 over 4 plus I sine 0 over 4. Okay, well, that wasn't so bad, was it? But are we done? Not quite. X to the fourth power means I need how many roots? I need 4 complex roots. I've found 1. Now what? Remember, we said the complex roots are evenly spaced points on a circle in the complex plane. The root we found is here, the fourth root of 8, or 1.68, units away from the origin. And at 0 degrees, since 0 over 4 is just 0, how would I distribute 3 more roots around this circle? To get 4 roots evenly distributed, they will be 90 degrees apart. So here at 90 degrees, here at 180 degrees, and here at 270 degrees. We'll use these angle measures to define the remaining 3 complex roots in polar form. I'm going to identify my roots with subscripts. So this first root I have will be called x sub 1. The next root, x sub 2, is the fourth root of 8 units away from the origin at 90 degrees. So it's written in polar form like this. The third of our complex roots is here. How do you think we write this root in polar form? X sub 3 is the fourth root of 8 times cosine 180 plus I sine 180. Our final root is here and is written x sub 4 equals the fourth root of 8 times cosine 270 plus I sine 270. Remember that we started this example attempting to solve the equation x to the fourth power equals 8. Our goal was to find all 4 of its complex roots, and what we've shown are the 4 complex roots that satisfy this equation. That is, each of these numbers raised to the fourth power equals 8. Pretty neat, huh? The process we just completed to find the fourth roots of 8 is generalized by a corollary to de Moivre's theorem, which states that the nth roots of a complex number z are equal to the nth root of r times cosine of theta plus 360k over n plus I sine theta plus 360k over n, where n is the index of the root and k equals the integers from 0 to n minus 1. This rational expression, theta plus 360k over n, is the algebraic process for finding the points evenly spaced around the circle like we did on the previous example. It takes the angle of your first root, theta over n, and adds increasing multiples of 360 divided by n, which spaces complex roots evenly around the circle in the complex plane. Notice that k stops at the integer before n. This is because our first root starts by adding a 0 multiple of 360, not 1. Let's use the formula to solve the equation z cubed equals 6 times cosine 120 plus I sine 120. To start, the formula says to find the nth root of the modulus. So I take the cube root of 6, which cannot be simplified. Then I use this expression to calculate the angles for each root. Since I'm taking the cube root, I will need 3 angles. I name them theta 1, theta 2, and theta 3 to keep my work organized. Theta 1 equals my original theta, 120, plus 0 times 360 all divided by 3, which is 40 degrees. Now, if you'd like to find the remaining 2 angles using the method from before, how far apart would each root be on this circle? 360 divided by 3 is 120 degrees, so each of our complex units will be 120 degrees apart. Since our first root is at 40 degrees, theta 2 will equal 40 plus 120, or 160, which is the same thing you get by using the formula. For the final root, I'd take 160 plus 120 to get 280, or you might use the formula to get 120 plus 360 times 2 over 3, which is also equal to 280. Our final step is to write each root as a complex number in polar form. So z1, z2, and z3 are the solutions to the equation z cubed equals 6 times cosine 120 plus I sine 120. We have worked through a lot of complex topics today. We practiced basic math operations like adding, subtracting, multiplying, and dividing with complex numbers in polar form. Then we derived de Moivre's theorem of finding powers of complex numbers in polar form. Finally, we used the corollary to de Moivre's theorem to find the nth roots of complex numbers. Great work today! Be sure to work through the activities and additional practice before attempting the online practice. See you next time! Hey, hey.